Okay, Unit 1, Part 5A, Digital Polysomnography. I've broken up the digital polysomnography presentation into two parts. The first will talk about general electricity things that are used in the lab, and the second will talk about data manipulation. And this is a lot of information to get through, and some of you might not understand it until we later explain things more. A lot of these things won't be on the exam, but it all comes from things that are on the exam. And also, if you understand the nature of electricity and that electricity is what we're looking for when acquiring sleep studies, you will be a super effective technologist who can fix things easily and run terrific studies. Polysomnogram is produced by a multi-channel recording instrument comprised of a hardware device, often called an amplifier, that interfaces with software to produce a digital record of the biophysical changes to the status of sleep during the course of a sleep session. Historically, polysomnographic records were conducted with analog equipment and physiologic activity recorded with pins attached to galvanometers onto paper. These machines were large and required replenishing paper and ink, and they had to have incredible storage facilities because each study was about the size of a couple large briefcases, and they had to be stored for a few years. And that doesn't include the film of the video recording. Because the activity was converted by mechanical means, each study required precise mechanical baseline calibrations. Calibrations make sure that whatever the input is, whatever we see on the display, is accurate. It actually matches. Scoring required page-by-page examination of each epoch, and events were marked and length calculated based on the timelines of the epoch. Then, on a log sheet, each epoch was assigned a sleep stage and any sleep-related event, which was all very time-consuming. These are the AASM requirements when it comes to technical specifications, and this is a good table to know for the exam. We'll talk more in detail about what each of these mean later, but you generally want an electrode impedance of no more than 5,000 ohms. Now let's talk about that. 5k ohm is the same thing as 5,000 ohms. So 5 kilo ohms, 5,000 ohms. Don't say 5,000 kilo ohms because that's totally different. The minimum digital resolution must be at least 12 bits per sample. The digital screen resolution must be at least 1600 by 1200, and the capability of a notch filter for each channel must be there. The time scale range window view must be able to show you at least 5 seconds to the most an entire recording in one window. The basic function of a sleep recording system is to record signals associated with specific physiological parameters and convert the activity into visible tracings that can be measured and analyzed. In polysomnography, there are three sources for these signals. We have bioelectric potentials, or biopotentials, transduced signals from sensors attached to the patient, and signals derived from ancillary equipment. So these are all three different kinds of signals. The first kind of electrical conduction is the actual electricity coming off of the patient. This means we can slap a wire over something along the electrical pathway of the person, or the signal pathway, to detect when electrical impulses occur. And that's a very simple way to put it. And we'll go on later about how different signals one wire can pick up and how to record just the waves we want. Anyways, the brain's electrical activity is the result of The brain's electrical activity is the result of electrical activity of neurons. Neurons are electrically charged or polarized, meaning they are either positive or negative, by membrane transport proteins that pump ions across their membranes. So when a neuron receives a signal from its neighbor through an action potential, it responds by releasing ions into the space outside the wall. ions of like charge repel each other, and when many ions are pushed out of many neurons at the same time, they can push their neighbors, who push their neighbors, and so on in a wave. Through volume conduction, the wave of ions reached the electrodes and a sensitivity or a sensitive amplifier. The measured difference in voltage between any two electrodes provides the EEG signal. That's what electricity is, the difference in voltage between two things. So if we had a reference electrode on the bone behind the ear, which is virtually zero, and we had an electrode on C4, and you compare those two electrodes, there's a number there. C4 at one time may read 50 microvolts. If you subtract that to the mastoid baseline 0, you get an output of 50 microvolts. The reference is there to provide a steady electrical zero baseline for use to compare the brain waves to. EEG activity always reflects the summation of synchronous activity of thousands of neurons that have similar spatial orientation. So anytime you're looking at the EEG, remember that the wave you were seeing is just an average sum of all the thousands of smaller waves that you don't see. The EEG we see are surface cortical brain waves. It doesn't account for deep brain stuff. For that, you've got to go to surgery. We'll also learn a little later about eye muscles and the front and back of the retina, which provides polarity or up and down, positive, negative for an eye EOG. The muscles that we look at for the EMG, which function much higher frequency than the EOG or EEG. And then finally, the electrical conduction of the heart. Remember, all of these things are electrical impulses or biopotential. The body produces them, and we're recording them as they are coming off the patient. Alternately, we can take made electrical signals out of something the patient does that we want to measure. Transduced signals are electrical signals that have been converted a different form of motion or energy to be recorded on the PSG. Very quickly, DC stands for direct current. That means when the circuit is closed, you get one voltage all the time, and the same for when you open the circuit. It's zero. It's either on or off. AC, or alternating current, gives an oscillating or on-off signal at a rate of 60 times per second, or 60 hertz. There are several reasons for the differences and where the currents originate from, but that's what you need to know for now. DC is on or off. AC goes back and forth at a rate of 60 hertz when the circuit is closed. Usually, transduced signals work with DC power. The electrical signal that we record come from the device with the transducer, not the patient. For example, when a patient snores, we use a microphone or snore sensor to record the vibrations. Snoring in itself is a sound. It's not an electrical stimulus. It's a byproduct of the tissue collapsing in the airway. So a snore sensor takes that analog vibration with a transducer. For now, let's think of a transducer as a magical box that turns one form of energy into another. In this case, a vibration or sound is being converted to ones and zeros digitally, so it can be displayed on the computer with our software. This is also the case with position sensors and respiratory sensors. And I promise we'll talk more about transducers later, and you will generally know how they work. Ancillary equipment would include pieces like a flow generator from a CPAP or the signal coming from a capnograph. A flow generator is something that is actually making air move. A capnograph has a vacuum, and it's actually sucking air in so that it can read CO2, and alternately CPAP goes the other way, and it's actually generating that flow. Breathing air or the concentration of CO2 in your respiration is not a function of electrical impulse as much as it is about gas exchange. So we have equipment that measures either the volume of our breaths or the volume amount of CO2 retention. That value from the ancillary device, the capnograph or the CPAP, is converted into a digital signal that is carried from the DC output box to the PSG software. Check this out. I'm kind of proud of this and kind of not. But this is a simple diagram of how the signal flows from the patient through the AC and DC equipment and eventually to the PSG computer. Please note that some of these external things can be incorporated into the head box itself, particularly the respiratory stuff. All that can be in the head box. That does not change the fact that those signals are still derived from a DC signal. So we have the patient hooked up to everything. And the signal pathway, here we are starting with the patient. So we have wires coming in from the head box, EOG, EEG, EMG, EKG. Those are going directly to an amplifier. The flow generators, external pulse ox, will go to DC. And like I said, these could be on the head box themselves. So, the EOG, EEG, EMG, those are all electrical signals coming off of the patient themselves. Those either go straight to the Ethernet router if they have the amplifier built into the head box. Next, in green, we have ancillary devices which measure things, non-electrical signals like CO2 or your pulse oximetry. These devices figure out the values we want themselves, and that data is transmitted to the DC box, which has sockets for inputs and sockets for outputs. The inputs are generally small headphone jack-looking wires, and the output is usually an Ethernet cable. Between these devices may be little boxes or special wires like patch cables that make the device connect to the DC box. A lot of capnographs have serial outputs. That's what these are, serial outputs. Those almost old-looking monitors. These are the DC wires. This is an Ethernet. The blue devices are transduce signals, meaning changing one form of energy into another. When you wear piezoelectric effort belts, the belts stretch a small crystal, which provides a small voltage which can be recorded. The bigger the stretch, the bigger the voltage of the signal, meaning we can determine how deeply a person is breathing as well as how often. These signals are all DC and can be on the head box or externally plugged into the DC box. Once everything is plugged into the DC box or the AC amplifier, those signals are taken through an Ethernet router, because you may have up to 3 or 4 Ethernet signals, depending on if the CPAP uses Ethernet output. The Ethernet router takes the AC and DC signals and sends it all to the PSG workstation computer where we can view the data. Take a moment to look at all the potential wires and connections that can be slightly unplugged or that could be broken. There are a ton. Here's a handy tip for when ancillary or transduced equipment for the DC box doesn't work. And how do you know that? If the PSG is not receiving that information, what you can do, unplug power to the amplifier, the head box, the DC box, and the Ethernet router, and wait 2 minutes. This will do something called a power cycle. And it's to totally deplete all of the energy from the chipboards and the power supplies on all these devices, and it resets the connection. And this has worked every time I've had machines that weren't coming through on the computer, and that ended up happening a lot. The first element of the signal pathway is the electrode coming off of the patient. The electrodes must have high conductivity to allow the signal to be picked up easily. For this reason, electrodes are commonly made of silver or gold. And gold is seen as superior because it optimizes the contact impedance over the long duration of a sleep study, and it will not tarnish like silver can. Here's a brief chart relating the comparable conductivity of different metals. Not really anything you need to know, but you can see that silver and copper are both more conductive than gold, but gold does the job very well. The signals all originate from the patient, and that's the pure source. Input signals from the patient are very small, so they have to be amplified and processed until they're strong enough and clean enough to be converted into a digital signal for visual display storage, or further processing and analysis. The electrodes are usually routed to the amplifier through a small portable junction box, sometimes referred to as the jack box or head box. Amplification is achieved through differential amplifiers, which can be integrated into the circuitry of a head box or a separate amplifier. All this information has to be transmitted from one location to another, usually with routers and cables. Each one of these separate components from the patient to the PSG computer screen has the potential to make the signal noisy or dirty. This is a very basic formula to figure out either the voltage or the current, where voltage equals V, current equals I, and resistance equals R. Ohm's law indicates that under conditions of constant voltage, meaning if a circuit's closed and we've got constant voltage going, if resistance is increased, current or flow of the electrons will be decreased. In the signal pathway, there are several factors that contribute to higher resistance, and technologists must be vigilant in decreasing these effects. We're going to have a whole part just on Ohm's law, so don't stress out about that too much yet. There are a lot of things that can make a signal's resistance higher. If an electrode cup is not completely filled, or if there is air in the conductive paste, that leaves room for electrons to flow differently. If the gold cup itself is damaged, or if the wire feels broken or bent or frayed, that allows for leakage current. Poor patient skin preparation will also not allow the electrode to pick up the scalp signals because of all the stuff in between the electrode and the skin. Same goes for topical creams and lotions that patients like to use. Sometimes alcohol and extra cleaning is needed to make the electrode impedance low, but also to get the tape to stick. This is a diagram of the signal pathway from the patient to the computer. VE could represent the exploring electrode, and VM represents a mastoid electrode. Those two are connected with a power source versus VS, and a referential electrode VREF, and is also connected to ground. Out of that combination, the desired output is displayed to the PSG monitor. A function of differential amplifiers is the cancellation out of unwanted voltages that are common to both input electrodes. That means if you got two electrodes and they both have these 60 hertz signal coming off, if they both have them and they're both equal, both of them will not be included in the output signal. If based on the ratio of the differential voltage gain to the common mode voltage gain. If the differential amplifier is perfectly symmetrical, the common mode gain would be zero, since both voltages would effectively cancel out each other, and the common mode rejection would be infinite. But in reality, there's a slight amount of common voltage gain, resulting in the industry standard ratio of 10,000 to 1, or even as high as 100,000 to 1. For sleep, it's 10,000 to 1 is the typical common mode rejection ratio, and that's what you need to know. We will talk more about common mode rejection. Because our bodies run on AC current, which alternates between voltage or polarity regularly and voltage, electrodes on the surface of the scalp measure analog signals from continuously changing voltage or amplitude as a function of time, meaning that they have cycles unlike DC. Differential amplifiers process the signals from two electrodes, an exploring electrode and a reference electrode, that can be considered electrical zero, or the electrical baseline, the reference that is. The processed signals are converted into a digital signal and recorded. There are a few different elements that can change the amplitude with differential amplifiers. Because one electrode value is subtracted from another, the distance of the exploring electrode from the reference on the actual brain waves can heighten or decrease the amplitude of the waves. So depending on how far apart the electrodes are on the scalp can make a difference in how big the waves are. When waves are above the baseline, we consider them negative in EEG. Let me say that again. When waves are above the baseline, we consider them negative in EEG. That's opposite of what we typically think. Usually if it's a upwards deflection, that's positive. Not in EEG, it's backwards. If the wave goes up, it's negative. If it goes down, it's positive. The positivity or negativity is called polarity. A differential amplifier works by subtracting the voltage of an electrical baseline like the mastoid from the exploring electrode to come up with a value, and that's what we see on a tracing. When dealing with EEG or sleep tracing, the V's are commonly referred to as G's. Voltage 1, voltage 2. When we see G1 and G2, that actually stands for grid. So if you have two areas that are of equal polarity and equal voltage, you should get a flat 0.0 signal. For instance, if you have two mastoids that are registering 50 microvolts, just for an example, it should be 50 minus 50, which would equal 0, and that cancels each other out. More likely, when dealing with EEG, we will have two electrodes with equal polarity and different voltages. When subtracting the reference electrode of 25 microvolts from the exploring electrode of 50 microvolts, you get a positive or downward deflection of 25 volts. This example shows two electrodes with opposing polarity and voltage. Be careful about the positive and negative symbols. If you have to subtract from a negative number, that means you are adding them. For instance, if negative 50 microvolts is subtracted from positive 50 microvolts, or 50 minus 50, you're taking away 50 minuses from 50 plus, that is 100. Positive 100. The wave deflects down, showing a positive deflection for EEG. Sometimes two electrodes with equal polarity and voltage both occur at dissimilar times, and that can shape the front and back part of a wave. It all depends on the time the voltages occur. If you were to plot dots at every 0.1 seconds of the voltage and then connect the dots, you would have brainwaves. That's essentially what the computer is doing. It reads two voltages and polarities, subtracts them, and plots with dots and connects them with lines. There are a lot of elements that can affect signal tracings. The location of the electrode and their placement compared to the signal source is important. If they're too far or not in the right place, the signal you're looking for might not come in through very well. This original signal source strength may also be very low or very high depending on what you're looking for. There are muscles all over the body, and those fibers twitch really quickly, and those signal sources are very strong. EEG sources are not as strong and not as quick, and they can be covered up by the muscle artifact. The location of reference and common ground electrode also can contribute to the signal. You don't want to have too much or too little distance between the two. Generally, the ground and reference should be approximately 4 to 8 centimeters apart, and I usually put them on the midline. So why don't we call the resistance against the signal being produced just resistance? Well, resistance is a measure of DC signals. Because there's polarity in cycles for AC signals, more components come into play and the resistance is more complex. So we call that impedance. The formulas for resistance and impedance are different. Every effort should be used to match input impedance of all electrode pairs as closely as possible. Typically, the lower the impedance, the better, but too low can have issues as well, like make the patient bleed. The general rule is to keep electrode impedance under 5,000 ohms or 5 kiloohms, but they should be relatively equal. If two electrode sites produce a signal with the same amplitude and frequency, but one amplifier input receives less voltage due to a higher electrode impedance, then the signals are not perfectly canceling out each other, and the effect of common mode rejection is reduced, which may result in artifact. An example of this would be 60 hertz artifact in AC, which we would use a notch filter for. Keeping impedances under 5 kiloohms reduces the chances for wide variation in impedances. So check it out. When I was where you were right now, I wanted so badly to understand everything about electricity because I understood just enough to think I could be good at it. When I got to AC power signals, capacitors, and impedance right here, my mind was blown and I couldn't figure out how any of it actually worked. And I occasionally go back and try and work on it to see if anything's changed. But my point is that most of these concepts, a lot of these concepts, are incredibly hard to understand even for the brightest minds. The people who operate these kinds of elements have brains who work differently, and that's great. We need them and we depend on them. But learn what you can and do your best. And if you do understand this stuff, well, daggone it, do something with it. How about it? Referential electrodes assist in canceling the noise and other voltages we are not wanting. They are most effective when placed on a side of the skull that is equidistant or equidistant from the exploring electrodes and also has a low impedance. For this reason, CZ is a good and commonly used location. Some systems have inputs for 2 referential inputs, thus allowing use for the best signal. Some acquisition systems allow the user to assign a reference electrode, thus alleviating dependence on referential signals that may go bad during the recording. The ground electrode is responsible for an electrical zero or baseline. Without a good, stable ground electrode, the exploring electrode pairs will not have a respective electric zero and therefore will wander with respect to equal inputs, thus picking up signals that would otherwise be canceled out. This wandering common potential may cause voltages at the amplifier inputs to exceed the zone where the amplifier is linear, causing amplifier saturation. Okay, that's enough of that. And that's the first half. Remember, you're not here to become an electrician. However, your job deals with electrical signals, and the more you know about electrical signals, the better you will be at troubleshooting artifact and getting the best studies you can.